Hello and welcome to the second AS Further Maths revision session for Callum Cymru. My name is Matthew McMillan. I'm a maths teacher at Christ College in Brecon. Today we're going to be looking at some questions involving proof by induction, and then in the future we'll be looking at momentum and impulse, and then the final session there's a live session where you'll have a chance to ask any questions that you may have. So, looking at the specification, there are three types of proof that we want to concentrate on, all with mathematical induction. So looking at how to prove the sum of series, the powers of matrices, and divisibility. Now, divisibility, we're going to do that first. Sums of series, we'll look at that second. The powers of matrices I have covered before last year, and if you'd like to do some more work on that, you need to go back and have a look at the 2023 video entitled Matrices and Sums of Series. The question was asked in 2023, a proof by induction on a matrix, so it's not impossible, but it's less likely to come up in 2024. It's more likely to be divisibility or sums of series. That does not mean you should neglect it, because they are allowed to ask anything on the specification. Something else that we've noticed in the teaching guidance on the right hand side is they've asked us to apply the proof by induction to the proof of the binomial theorem, which I will also spend a little bit of time having a look at. Okay, so we'll start with a divisibility question. This is a fairly typical question. It's taken from the exam board 2017. Use mathematical induction to prove that 9 to the power of n minus 1 is divisible by 8 for all positive integers n, and it's 7 marks. On all these questions, you start with a basis step, which I've written. We just substitute the number 1 into whatever is given, and hopefully we show what they're asking for. In this case, we get 8 coming out. You do want to add a statement here, so something along the lines of this is divisible by 8, and therefore it is true for n equals 1. Don't just leave it there. Next up is an assumption step. So we make a statement, we assume it is true for when n is any value, such as k, and then just write n to the power of k minus 1 is divisible by 8. We're replacing basically any sort of letter in here with a k. And then we're on to the induction step when n is k plus 1, so the next one in the sequence. There are a few ways that we can go about doing this. Something that might be useful is just taking this and thinking if this is true, this means that 9 to the power of k minus 1 is equal to 8 times something, because it's in the 8 times table. And if we continue with this, we get 9 to the power of k equals 8n plus 1. We're going to sort of use that in a minute. For the induction step, I'm just going to sort of do it down here, otherwise I'm going to run out of room. We change the k to k plus 1 minus 1. And then we're just going to deal with the index here. So 9 to the power of k plus 1, using our laws of indices, this would be 9 to the power of 1 times 9 to the power of k. That's what that is, isn't it? Because using your laws of indices, you add the powers. So what we're actually getting here is 9 to the power of 1, but I'm not going to write the 1, times 9 to the power of k minus 1. This 9 to the power of k bit here, we could substitute in 8n plus 1, and then let's see what happens. So 9 bracket 8n plus 1 minus 1, and then let's expand it and see what happens. 9 times 8, so we get 72n plus 9 minus 1. So 72 and 9 plus 1, 9 minus 1, so that's 8. we get 72n plus 8. Let's just make it really explicit that this is in the 8 times table, so we want to factorise out an 8. So we get 8 bracket 9n plus 1. That is definitely in the 8 times table, so we'll just make a statement which is divisible by 8. So the induction step is usually the slightly more tricky bit, and then we have a conclusion step. This is just ripped straight from the mark scheme, and we basically are saying, hence it is true for n equals k. This implies that it is true for k plus 1, and because it's also true for n equals 1, the result is proved by induction. Now, the way that I've done it here, there are alternative ways that we could approach this. So if one other alternative method is, if I think about a times table such as the 8 times table, which would look like this, 8, 16, 24, etc. It's always going up by 8. Even if it's not the 8 times table, let's say we are going from 8 to 24, it's going up by 2 times 8. So it always goes up by some multiple of 8 each time. So an alternative way of doing this might be to say, for the induction step, you could say that when we have 9 to the power of k plus 1 minus 1, and we find the difference from the term that came before it, which is 9 to the power of k minus 1. That difference, a bit like what I've got going on up here, that difference should be in the 8 times table. So we would get 8 to the power of something. You could use an n or something like that. And then we're thinking about the difference, and we want to show that that difference is in the 8 times table. I'll just go ahead and continue with this. So this 9 to the power of k plus 1, we're still going to break it down into 9 times 9 to the power of k minus 1. Take away, and we'll multiply this out, so we get 9 to the power of k plus 1 equals 8 to the power of something. And then how many 9 to the power of k's have we got? Well, we've got 9 of them here, and we've got 1 of them here that we're subtracting. So eventually we've got 8 9 to the power of k's. Minus 1 plus 1, well, that's 0. So that is 8 to the power of something. And then we can go ahead and make a statement saying that this is in the 8 times table, or the difference is in the 8 times table. That's just an alternative way of doing it. So that's a divisibility question using mathematical induction. And we'll just put another one on the next slide. Okay, so we have another divisibility question on the screen. You might like to pause the video and have a go at this one. And then I'll just bring up the mark scheme. There we go. It's an older mark scheme. It's still the same concepts, and you can see you're getting marks for each step. They do it slightly differently, but it's still the same concept. Here, I was saying this is something in the 4 times table, so we could say it is equal to 4 times n, or 4 times something. And then it's down here, we just want to have a think about how can we break this up into, I want to try and introduce this bit here somehow. So they've kind of skipped a little bit because it's just a mark scheme. But I guess we're looking at this first bit and we're saying that that is 8 times 9 to the power of k plus 1 times 9 to the power of k. And then the other bit is 4 times 5 to the power of k. Plus 1 times 5 to the power of k. And then I guess they've tried to group together these bits here because we kind of want to get that bit, because that is the bit that equals 4n, and then we want to show the other bit is also some kind of multiple of 4, or overall we have a multiple of 4. I'll just continue with this. So what would we get here? We would get 8, 9 to the power of k minus 4, 5 to the power of k plus 9 to the power of k minus 5 to the power of k. And then this first bit at the front, I might be saying, well, this is in the 4 times table because we can extract a 4 out, because we get 4 times 2 times 9 to the power of k minus 1 times 5 to the power of k. And then this last bit is also in the 4, oh, close the bracket. This last bit must also be in the 4 times table because it's what I established at the very beginning, that is 4 times something, and you're making a comment about along the lines of both of the parts are divisible by 4, or the whole thing is divisible by 4. Okay, it's just a slightly older mark scheme, but it's still the same concept. It's slightly more tricky as well because we have 2 numbers here with a power of n on, but that's another divisibility type of question. Okay, so that covers a couple of questions on divisibility. Now we're going to have a look at proof by induction of the sums of series, and I've also found an interesting question involving sequences which we'll have a look at, and then we'll finish off by looking at a proof by induction of the binomial theorem. Okay, so here we have a fairly typical sums of series type question. Use mathematical induction to show, and then you get a sum of a series written in sigma notation, which you should be familiar with. And it says we can expand that and we get a kind of generic solution. We start as per normal with basis step. For this one, it seems to make sense to I sort of concentrate on the left hand side and the right hand side separately. So that's what I've done. This bit here, I guess, is going to be 2 minus 3 times a half. So 2 take away 1.5 would still give me a half. Look at the left hand side and the right hand side separately, and then just say they're the same. Therefore, it's true for n equals 1. For the assumption step, I'm kind of looking at my expression, and I'm basically saying I want to change all of the n's for the letter k, because ultimately I want to replace all of them for k plus 1 in the induction step. So that's what we've gone ahead and done. And then we're on to the induction step, where it starts to get a bit trickier. So when n is k plus 1, we've changed here for k plus 1, and we know that when we just have it as a k, this is what we get coming out, 2 minus k plus 2 times a half to the power of k. So that would take us to the kth term, but then we need to add on one more extra step of the sequence or series, and each step of the series is given by this formula. So it's r. Now in our case, the final step of our series is given by k plus 1. So I'm replacing that r for k plus 1 times 1/2 to the power of, and this again will be k plus 1, because that's adding on like the last term. So we've got the sequence up to this value k, and then we're adding on the last term of the sequence, and that's kind of our starting point. Then we just want to go ahead and we want to try and make it look a bit like this expression over here, but with all of the k's replaced with k plus 1. So that's what we're going to go ahead and try and do. I think what I have done is I'll just keep this as 2 minus k plus 2 times a half to the power of k plus k plus 1 times, and I'll break this power of k plus 1 up as 1/2, and then 1/2 to the power of k. It looks here like I've got a half, sorry, not a half. Looks here that I've got a half to the power of k that I could factorise out of these two bits. So that's what I'm going to do to start with. So we've got 2 minus half to the power of k, and then open my brackets, k plus 2. So that's kind of that bit there dealt with. Now I have to be a little bit careful here, because when I'm sort of factorising out this half k, the power that's the positive symbol that's in the middle here is going to become minus k plus 1. Actually, I'm going to keep that in brackets, times a half. And if I don't do that, this here, this little change, is because we're multiplying at the front here by the negative. So it's going to become negative times negative. That would give me that positive. I'm going to continue just over here. You should probably continue down the page, but I don't have space. So 2 minus 1/2 to the power of k. And then let's think about what's going to happen here. So dealing with the k's, I've got a k minus half a k. So that's going to give me half a k. Half k. And then dealing with the numbery bits, I've got 2 here. 2 minus 1 times a half, so that's 3/2, plus 3/2. And I think we're nearly there, so 2 minus half to the power of k. If we extract a half out as a factor from this bracket, then we get a half times k plus 3. And I think we're kind of there. We just want to make it look a little bit more like what we started with up here. So we're getting 2 minus this k plus 3 bracket. I'm going to break that up into k plus 1 plus 2. So that's this bracket here, and I've just changed the k for k plus 1. And then we've got a half to the power of k plus 1, because my k here and my half to the power of 1 here, I've just added the two powers together. And I'm just going to double check what I needed it to look like. That k I've changed for a k plus 1, that k I've changed for a k plus 1. So true for k plus 1. Then, as per normal, just a conclusion step to finish off. Okay, so I found this interesting question, one of the past papers. It's not really a sum of a series or a divisibility question, but I thought it was interesting anyway, and maybe we should just take a look at it in case you come across something in a sort of new scenario. So we have a sequence, and it's generated by this relationship, and we'd say this is a recurrence relationship. It's telling you how to get from one term to the next term in the sequence, and it says that x1 is equal to 3. You could go ahead and find what x2 is, etc. And sometimes it's quite interesting just to do that. I've worked them out, I've got them written down here. So we've got x2 we worked out as 6, x3 you can work out as 11, x4 we can work out as 20, and x5 is 37. Obviously you could keep going just to see what's going on with this sequence. And what they're saying is that down here we've got another way of writing the sequence, and this is the nth term of the sequence. So if we put a 1 into this formula, 2 to the power of 1 plus 1, that should equal 3. And if we put a 2 into the formula, 2 to the power of 2 plus 2, that should equal 6. 2 to the power of 3 plus 3 equal 11, etc, etc, etc. So they're kind of taking a recurrence relation and turning it into an nth term, and I thought it was an interesting question to have a look at. As with all proof by induction questions, we'll start with the basis step, and you put 1 into the expression, which is what I've done up here, and I've put it into the nth term. Now I've said it equals 3, and it is true because they've told us the first term is 3. Our assumption step, so we're concentrating on the nth term, and we're saying we are replacing the n's for k's. Ultimately, what I would like to do, and sometimes it's worth writing this, is thinking about what do I want to get. Ultimately, I want to get this. I want to get x k plus 1 equals 2 to the power of k plus 1 plus k plus 1. Okay, I need it in this format, but with all of the k's replaced for a k plus 1. That's what I'm trying to achieve. So in my induction step, it would be great if I had some kind of expression that explained how to get to the next term, and because they've given you that at the top, that is where we're going to start from, using this recurrence relation. So using this bit here, I'm going to write x and then subscript k plus 1 equals, and I'm kind of copying it across, 2. Now x k minus k plus 1. So I'm just replacing the n's here with a k. What would be nice is if I had an expression for x subscript k, and I do, so I'm going to replace the xk for that bit there. So x k plus 1 equals 2 bracket 2k 2 to the power of k plus k minus k plus 1. Now, if I multiply through the 2 times the 2 to the power of k, that gives us 2 to the power of k plus 1. 2 times 2k, so we get plus 2k minus k plus 1. So x k plus 1 equals 2 to the power of k plus 1. And then 2k minus k, so that's plus k plus 1. So it is true for n equals k plus 1. So that's the inductive step, and then you finish with your conclusion step. And I thought that was just a nice additional type of question, and it'd be worth just having a look at that. Okay, so we're going to have a look at proving the binomial theorem using proof by induction. It's not immediately clear. If we look down at the bottom here at the specification, it's not immediately clear that this might be examined. It says to explore the sums of series, the powers of matrices and divisibility. But in the teaching guidance, it does explicitly say an application to the proof of the binomial theorem. And it says for a positive integral power, so we're basically saying that when that power is a positive integer. If you, when you get into year 2 of your A-level course, you'll deal with situations where that is not, where that is fractional, where it is negative, but we're not dealing with that here. There's quite a few bits of information here that you will know and recognise, but this up here, this is Pascal's identity, and this is where this comes into play. I haven't found any past paper questions on this topic from our exam board or any other exam board, so I'm not quite sure how they'd present the question, but I'll run through a proof that I found and I quite like, and then at least you've got the information. So up the top here is Pascal's identity, and it's given to you in the formula book. You might want to just have a think about what it means. So if we draw Pascal's triangle out, let's go to maybe the 5th or the 6th row. Yeah, let's go down one more. 1, 5, 10, 10, 5, 1. Because a nice way of just explaining what this is talking about is just using the triangle. So here we have our 0 row, 1 row, row 2, row 3, row 4, row 5. And then we also have columns. I guess this is kind of like column 0, 1, 2, 3, 4, 5. If we take, for instance, this here is 4C1, and if we take this one here, this is 4C2, and what the identity on the right hand side is saying is if we take 4, 1 and we add 4, 2, we should get, so it looks like I have to add 1 to the number at the top, so we should get 5, and I keep the number the same. This number here should be the same, so I should get 5, 2. Let's just see what happens there. So 4, 1 is the number 4, 4, 2 is the number 6, and where do I get taken to? I seem to get taken here, 5, 2, which does equal 10. So using the triangle, we can see how that identity works, and that's probably the nicest way of seeing that. You can prove it algebraically using this. It just gets a little bit more awkward. Also, if you go and Google this online, you might find this written in a slightly different format, but the concept is the same. So that's Pascal's identity. We're going to need that, but because it's given to you in the formula book, I don't think we're going to need to prove that. Other things that we want to remember are when we are dealing with this bit here, this is 5, 0. This bit here, that is 5, 5. And both of those are both equal to 1. We could go to, I've sort of written it here, we could go to 6, 6, or we could go to 6, 0. Both of those will be equal to 1. We're basically saying the whole of this diagonal and the whole of this diagonal, they will always be equal to 1. And that's just something else that we want to remember when we're doing this proof. Okay, so on to proving the binomial theorem. Like I said, I haven't found any exam questions on this. I'm not quite sure how they'd ask it, but we'd start our proof as with any proof by induction, when n is 1, and you'd say a plus b to the power of 1 will equal a plus b, so it's true for n equals 1. And then we'll put our assumption step in, so assume the formula works for n equals a value, such as 1 or 2 or 3, but k. What I've decided to do though, and it sort of works nicely with the proof, is I've decided to keep the first 3 terms of the series, which is actually what they've got in your formula book. I've decided to keep the middle term. Again, that's what they've got in the formula book. Slightly different to the formula book, though. I've decided I'll keep the last 2 terms because I think it might be interesting to see what pops out. So the induction step, when n equals k plus 1, we will have a plus b to the power of k plus 1 equals a plus b to the power of k times a plus b. So we're going to multiply what we've got above by a, and then multiply what we've got above by b. what I'm going to do is, just to make it kind of stand out a little bit better, is I'm going to do everything that I multiply by a, I'm going to do it in red. So I'm going to take the first term here and multiply it by a. So we get a to the power of k plus 1. And then I'm going to take this second term and multiply it by a. So you can see the k1 will remain the same. The a to the power of k minus 1, because we've added 1 to the power, it's just going to be a to the power of k. And the b is staying the same. And then I'm going to multiply this bit here. So we get k2. And we've added 1 to the power. So instead of k minus 2, it's k minus 1 times b squared, add dot dot dot. And I'm going to skip along to this term, k r times a to the power of, now because I'm multiplying by a, this is going to be k plus 1 minus r, b r plus, in fact I should put a plus there, dot 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 plus k minus 1, a to the power of, or 2, b k minus 1 plus a b to the power of k. So that's everything multiplied by the a. Then I need to multiply everything by the b, and I'm going to do that in green. So what will we have? So we're going to do b times that. So I'm going to get plus a to the power of k times b, because I've times it by b. And then here we've still got k1 a to the power of k minus 1 b to the power of 2, and then let's multiply this bit. In fact, I'm not going to multiply it. I'm actually going to be a bit naughty. I'm going to skip here. The reason I'm skipping is because I start to see a pattern, and it's to do with how I've written these. Can you see this bit here and this bit here? The a to the power of k minus 1 and the a to the power of k minus 1 seem to match up, and the b to the power of 2 and the b to the power of 2 seem to match up as well. The only slight difference is the k1 and the k2, but we'll deal with that in a minute. You can also note that these two here kind of match up. So I'm going to be trying to match up the red bit with the green bit. I think for this it might be helpful if I just wrote what would be here. That would be k0. That might help it match up a little bit better. And remember that k0 is just equal to 1, so I am allowed to write that there. Bearing in mind this is the way that I'm going to match them up, I am interested in skipping to what would match up with this bit here and having a think about that. So what would match up with that? Well, we would have the term before would be k r minus 1, because it's the term before. The term before would be, because this term here has been multiplied by a, I kind of want to think what would have come before this term, and before that term we would have had a k plus 1 minus r. Well, that's nice because it does match up with that. And then I'm multiplying this term by b, but what I also want to think is what was the term that came before this? Well, the term that came before this was b to the power of something before that, so we're going to get here b to the power of r, because if I multiplied this by b, I would have got b to the power of r plus 1, and I'm thinking what comes before that. Plus, so now I do have a pairing up, dot dot dot, and again I'm kind of thinking of pairing these two up, but I can just do this by looking at what I've got here. So timesing this by b, I've got k minus 1, in fact I should put plus there, a b to the power of k plus b to the power of k plus 1. Now, looking at these last two bits here, because I'm pairing them up kind of with the term above that came just next along in the sequence, here I think I want to put here k. That will allow it to pair up a little bit nicer, and remember that kk equals 1, a bit like down here, k0 also equals 1, so we're allowed to write them in there. Now I'm going to kind of pair them up. It's getting a little bit messy now. So the a to the power of k plus 1, that just stays as it is, a to the power of k plus 1. Pairing these up here, do you see the a to the power of k times b and the a to the power of k times b? They're common, so we'll just write a to the power of k times b. The bit that isn't common is the bit, the k1 and the k0. So I'm just going to write k0 plus k1. So that's that bit dealt with. I could continue then. What are we going to get next? We're going to get a to the power of k minus 1, b to the power of 2 times, and this time it's going to be k1 plus k2 plus dot 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 plus, and then we've got a to the power of k plus 1 minus r times b to the power of r times, and then we've got k r minus 1 plus k r. So that's pairing up this bit here and this bit here, plus dot dot dot, and then I'll just pair up the sort of penultimate term here with the last term here. So we've got a b to the power of k times, and we've got k minus 1 plus kk, and then finally b to the power of k plus 1. Now this is looking good, because we're looking here at Pascal's identity, and that's what we're going to apply to each of these bits in the brackets here. And remember, ultimately we want all of the k's that were here to be a k plus 1 ideally. I will also explicitly write this as k plus 1 in there, just to make it obvious. I might have k plus 1 minus 1 in my answer. So here we're going to get a to the power of k plus 1, that's good because we've changed the k into a k plus 1, plus, and then here using Pascal's identity, I can see the single k and the single k, that should turn into a k plus 1, k plus 1, and then the number at the bottom is whichever one is higher, so it's the 1. And hopefully you can sort of see that here the k has turned into a k plus 1, but the 1 has remained the same. So we get a to the power of k plus 1 minus 1, and that's because I want it to look in this format. You don't really have to do that, times b plus k plus 1, 2, a to the power of k plus 1, maybe I could put that in brackets actually, minus 2, put that in brackets there as well, b to the power of 2, plus the middle bit, which is k plus 1r, a to the power of k plus 1 minus r, b to the power of r, plus dot dot dot, plus k to the power of kk, a b to to the power of k plus 1 minus 1 plus b k plus 1. Hence, true for n equals k plus 1. And then finish off with a conclusion step. There are multiple ways of proving it. You can go and look online and find a lot of videos showing how to do this proof by induction, but this one was the one that I preferred, the way of matching up one term with the previous term. It's similar to how we look at a lot of sequences and series questions, and so this is the one that I liked the most. So that covers divisibility and sums of series, as well as looking at the binomial theorem for proof by induction. Like I've said before, if you need to revise questions involving powers and matrices, you need to go back to the video from 2023 and have a look at that. Now, in the next session, I will be looking at momentum and impulse. And in the final session, we will have a live session where you're welcome to ask any questions, and we'll also have a look at Hooke's law.